This is Daryl with Network Systems. For today, we're going to go through the TCP/IP protocol stack and the internet in 2 hours. This is a quick survey. We're going to go through the network layers, including the physical layer, the link layer, the network layer, and the transport layer. We're not going to cover the application layers today. Today is an overview. We'll cover each topic in more detail later in the course. I encourage questions. And for the first lecture, this is a double lecture today, so we have no lab today. The network has one mission: get the data to the destination. We have a bunch of overlapping complex protocols that we're going to learn, but in the end, it is all about a process on one computer sending bytes of data to a process on another computer. When talking about network protocols, it is helpful to categorize those protocols into different layers. The OSI has a 7-layer theoretical model for talking about networks. We'll start at the bottom. The physical layer deals with encoding bits onto the wire, or bits onto the fiber, or bits into the spectrum. The data link layer, which is layer 2, deals with directly connected node-to-node data transfer. And when we talk about bits, when we talk about data being transferred, we talk about it in units. And at the data link layer, the unit we use is frames. Layer 3 is the network layer. This is end-host to end-host data transfer. And our units at the network layer are packets. The transport layer is layer 4, and that transfers data to an application via a connection. And 2 of the common protocols are transmission control protocol or user datagram protocol. The transport layer is getting the data to the application, so it's getting it to a process on a computer. We have the session layer, which establishes multiple connections between applications. Occasionally you will run into a protocol which has multiple sessions, multiple connections between 2 processes. We have the presentation layer, which deals with data encoding and representation. So ASCII representation, SSL, encryption. And then there's the application layer itself, the 7th layer of the OSI model, which of course is the application, the end application that is using the other layers. Each layer uses the services of the layer below it to get data to the destination. So the data link layer is using the physical layer to get data to the next node. The network layer is using the data link layer to get packets to the end host. The transport layer is using the network layer to get to transfer the data to the end application. The OSI 7-layer model is a theoretical model. There is also the TCP IP protocol suite has its own layered model, and it uses a 5-layer model. The 5-layer model, starting at the top, we have the application layer, which includes all of the session creation, the presentation, data formatting, and then the application itself that you would see in the OSI 7-layer model. And applications use the transport layer, which is end-to-end process communication. The transport layer uses the internet layer, which is host-to-host packet communication. The internet layer uses the data link layer, which is node-to-node, which is your local area network, individual hops getting to the end destination. And then the data link layer uses the physical layer, which is, of course, copper, fiber, spectrum, and encoding bits onto those. TCP/IP used to be called a 4-layer model when the data link and the physical layer were merged into one, which was called network access. So you might find references of the TCP/IP 4-layer model, in which case it would be network access, internet, transport, and application. And one key difference of TCP/IP versus OSI is TCP/IP, the 5-layer model, is actually implemented. And we're going to learn about those protocols and use that implementation in this class. Here are some examples of the physical layer. Coaxial cable. You may have a cable internet access at home, and that coaxial cable is a good example of a physical layer providing network connectivity to your home, and that'd be an example of a wide area connection, although it could be used for local area connections as well. Category 3 copper is low quality 2 twisted pair Ethernet. So here's an example. You can see we have 2 pairs of cable inside this particular run. So actually, yes, I see 4 wires total. So this is category 3 wire. In fact, you can see Cat3 on the label right there. And that's good for 10 megabit Ethernet. We have Cat5 and Cat5e copper, which is 4 twisted pair, which is rated at 100 megahertz, which is good for Cat5e is good for gigabit. Cat5 is good for 100 megabit, although often people end up running gigabit on Cat5. And that is 4 twisted pairs. And so if you look close enough here, you'll see that there are 8 wires, so there's 4 sets of twisted pairs here. There are improved categories of wire, Cat6, Cat6a, Cat7, Cat8, that are used for faster and faster Ethernet connections. So for example, Cat6a can run 10 gigabit over short distances and is used in data centers. Most new buildings, when they're installed today, are installed with some variant of category 6 copper. We have multi-mode fiber, single mode fiber. There's many different grades of the fiber. Here we have an example. The orange run is multi-mode fiber. The yellow run is single mode fiber. There's actually a strand of glass inside this fiber strand, and the glass can bend, but you can't bend it too much or it will degrade and break. And each fiber connection usually uses 2 strands of fiber, one for send and one for receive. Although it is possible to send and receive on 1 strand of fiber if you have the correct and more expensive piece of network equipment. This here is actually what's called an SFP, and it has a laser in it which is shooting, or a light emitting diode or a laser which is shooting light down the strand of fiber, and then on the other strand it is receiving the data. And then of course the other physical layer, which we all use all the time, is wireless spectrum. You can use infrared or you can Wi-Fi, for example, can use frequencies in the 2.4 gigahertz band or in the 5 gigahertz band, and there's a new standard that uses the 6 gigahertz band, although it's not commonly used yet. These are all examples of physical layer, and all of the other protocols that we're going to learn, in the end, they run on top of the physical layer. A link layer protocol is a protocol that runs on top of a physical layer. The purpose is to communicate between directly attached hosts. The protocol depends on the physical layer. So different physical layers, your link layer protocol adjusts to handle the limitations of that particular physical layer. Link layer protocols have different ranges depending on the physical layer and the design of the protocol. Here are some examples. Ethernet, and Ethernet can run on top of copper or fiber, different types of fiber. Digital subscriber line, cable internet, also called DOCSIS, can run on top of the coaxial cable. Wi-Fi, also called wireless Ethernet. Packet over SONET. FDDI, which is a fiber distributed data interface. the point-to-point protocol, which used to run over telephone modems. We have token ring, which is now an obsolete physical layer, which was an early competitor to Ethernet. This is a diagram of the early Ethernet physical infrastructures. They were called 10^5 or 10^2. They ran at 10 megabits per second and could run 500 meters over a thick coaxial cable or 200 meters over a thin coaxial cable. Each computer had a network interface card and connected to the coaxial cable in a bus. So each computer, the network interface card, could transmit bits as electrical signals on the bus, and every other host would be able to see all the bits on the bus. The groups of bits transmitted on the bus to send one message is called an Ethernet frame. Stations will sense if the bus is in use before transmitting. That's called carrier sense, and only transmit if the bus is not in use. However, it's still possible to have a collision because signals transmitted from one station may not have reached another station when that station believes that the bus is inactive. So all stations have access to the bus simultaneously. It's called multiple access. And it's still possible, even with that sensing, carrier sense, that two stations may simultaneously transmit. If that happens, there's a collision. The data is garbled, but both stations are able to detect the collision. That's called collision detect. So as a result, we have a term: carrier sense multiple access collision detect, CSMACD. That's a fundamental feature of the original shared Ethernet. You can sense if the bus is already in use. Multiple hosts access the bus simultaneously. It's still possible when transmitting to have a collision, but you can detect it. After a collision, both stations delay a random amount of time and retransmit the data. There's no central coordinator for Ethernet. In Ethernet, if you have data and if the bus appears quiet, then you can transmit. If you collide, then you wait and retransmit a random time later. This is the original Ethernet physical infrastructure, and we're well past this shared bus infrastructure today. However, this technique of detecting that a collision occurred and retransmitting is very useful for Wi-Fi, and in fact that's one of the reasons why it's called Wi-Fi Ethernet. Over to the right we have a picture of a thin coaxial cable where we have the lines that are running, and then you have a T connector, and then the T connector will plug into the network interface card on a computer. At the end of the line, you wouldn't have this extra cable, but you have to have what's called the terminator, which is a resistor which prevents the electrical signals from reflecting. If somebody were to take off that terminator, then the electrical signal would reflect, and every transmission would appear to be a collision. That made the original 10^5, 10^2 Ethernet very fragile. Simply unplugging one wire at any place along the entire bus would result in the entire network going down, which was undesirable. And early in my career, I personally had to troubleshoot one instance where a whole LAN went down, and we'd have to go around and try to figure out, which component was unplugged. Ethernet frames have a format, and the format includes a destination address. Network interface cards listen for specific destination addresses, and if they see a frame with one of the destination addresses that they are programmed to listen to, then and only then they will pass that frame up to the CPU. A network interface card will listen for its host's own unicast destination address. It will listen for the broadcast Ethernet destination address, which is all ones. And hosts can also subscribe to multicast addresses, which we'll cover later, but at the Ethernet level it just means, hey, here's another pattern of destination addresses, and if you receive any of these, then pass the frame up to the CPU. A network interface card can also be in what's called promiscuous mode, which means that it will attempt to collect all frames, or at least attempt to collect all frames, and pass that up to the CPU. If you are monitoring network traffic and trying to capture network traffic, you have the option, using a tool such as Wireshark, you have the option of putting the network interface card in promiscuous mode. So in that case, you'll capture any traffic that passes by your network interface card, whether or not the destination MAC address is your own MAC address. Ethernet addresses are 48 bits. Here is an example of an Ethernet address. It is 48 bits. And it's also called a MAC address, media access control address, or a hardware address. It's the default Ethernet addresses are built into the network interface card when they're manufactured in the factory and are globally unique. But again, you can, with some operating systems and some network interface cards, you can reprogram them, and you can, of course, subscribe to multicast Ethernet addresses, which are other Ethernet addresses. There are multiple Ethernet frame formats currently in use in the Internet. However, the Ethernet 2 frame format is dominant and is used for most protocols. On any particular Ethernet network, it is possible to see the other frame formats, such as the 802.3 format or the 802.2 format. However, those formats are only used for a few protocols. And what's interesting is on a physical Ethernet network, you might have examples of one Ethernet frame format go by, and then an example of another Ethernet frame format go by. And later in the course, I might show you an example of that. However, 99% plus of the frames that you're going to see are the Ethernet 2 frame format, which we're going to cover in detail. The Ethernet 2 frame format starts with a preamble, which is 7 bytes, with the bits alternating 1 zeros. And then it has a start frame delimiter, which is 1 byte, also has bits alternating 1 0, that then ends in 1 1. And it ends with a frame check sequence, so that way if the frame is corrupted, the network interface card can detect it and throw it out. And then there is a minimum interpacket gap between frames. That's the frame format as seen on the wire. Inside the frame itself, which is what the network interface card will pass up to the host, is the destination MAC address, which is 6 bytes, 48 bits. The source MAC address, 6 bytes, 48 bits. The type, which in Ethernet 2 frame format, the type is the contents of the, which tells what type of data is encapsulated in the Ethernet 2 frame. And then the data itself can be from 46 to 1500 bytes. And if the data you want to send is smaller than that, then it will add a little bit of padding so that each Ethernet frame has a minimum size. If the types are all programmed to be greater than size 1500 in decimal. If you run into a 2-byte field healer which is less than 1500 in decimal, then it is not an Ethernet 2 frame, it is one of those other frame formats. And we're not covering those other frame formats in this course. Just know that the type field, if it's less than 1500, it is not an Ethernet 2 frame. And 1500 is 05 DC in hex. I hope you're all familiar with hexadecimal math. In hexadecimal math, a hexadecimal digit ranges from 0 to F, which corresponds to a decimal value of 0 through 15. We are going to deal with a lot of packets and a lot of bits in this class. To make the packets or bits easier to represent, we're going to display them as hexadecimal digits. So when you see a hexadecimal digit, I want you to think that that hexadecimal digit corresponds to 4 bits. Every hexadecimal digit corresponds to 4 bits. So in that sense, hexadecimal digits are equal length. The only question is which 4 bits. For example, C is 12 in decimal. In bits, we have the 1 bit, we have the 2 bit, we have the 4 bit, and we have the 8 bit. So 12 is 8 plus 4, so we set the 8 bit to 1, we set the 4 bit to 1, and then the others are 0. So a C in hexadecimal corresponds to the bits 1, 1, 0, 0. Here we have 48 bits, and we convert them to the hexadecimal digits. So for example, 0101, well, we have the 1's bit, which is set, the 2's bit is not set, the 4's bit is set, the 8's bit is not set. So 1 plus 4 is 5. That's our hexadecimal digit 5. Here we have 1101. 1, not adding 2, adding 4, adding 8. So 8 plus 4 plus 1 is 13, which is D in hexadecimal. And so on. So that way we can convert the 48 bits into hexadecimal characters. How many hexadecimal characters do we have? Well, each hexadecimal character is 4 bits. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 hexadecimal digits. So that is 48 bits. So in the prior slide, we had an Ethernet MAC address, which was 48 bits. And here is the same Ethernet MAC address represented as a hexadecimal digit. Let's show different ways to show Ethernet addresses, or hardware addresses, or MAC addresses. Those are just different ways of saying the exact same thing. The address is 48 bits, which is 12 hexadecimal characters. We have 6 octets. Each octet has 2 hexadecimal characters, so each of these octets is 8 bits. That's why they call it an octet. 6 times 8 is 48. And we can some operating systems separate them with colons every octet. Some operating systems separate them with dashes every octet. Some operating systems separate them with dots every 2 octets. So in fact, actually, this would be a hextet because it has 16 bits. So 16 plus 16 plus 16, also 48. Let's review our first tool. On Unix, it's called Ifconfig-A. So it's the Ifconfig, and the -A means it prints out all information about all network interfaces, even virtual ones. If I run that on my Mac, I get an LO0 interface, which is the loopback 0 interface. And I have some other logical interfaces, GIF0, STF0. I have EN5, which is a type of Ethernet interface. And you can see here I have an Ethernet address. So there are the 48 bits that we're coming to know and love. I have an AP1 interface, which also has a Ethernet address. Notice that it's a different Ethernet address. Each network card, each network interface has its own Ethernet address. And then we have EN0, which has an Ethernet address, 48 bits. One thing that can be difficult on some operating systems is figuring out which interface is actually used for internet connectivity. In this case, my EN0 interface is the one that I'm using for internet connectivity. And the reason I know that is because that is the interface where I have internet route, where I have IP addresses that are usable. I have this 192.168 address. I have my internet routable IPv6 addresses. So I have, just by looking at this output, I have a high degree of confidence that the EN0 interface is being used for internet connectivity. Meanwhile, up at the EN5 address, I don't have an IPv4 address, My IPv6 address is not internet routable. You don't know that yet. We're going to learn that in this class, but just by looking at it, I can see that the EN5 address is not being used for internet connectivity. The LO0 address is the loopback address, and it's used for local testing. So if you send a packet to 127.0.0.1, which is the well-known IPv4 loopback address, the packet will be sent on your computer, but also received on your computer. So as a programmer, that's useful to you because you can run applications and you can test them. If you have a client and a server application running on the same computer, you can test them both. You can test them by setting 127.0.0.1 as your destination for your network communication socket. So ifconfig-a on Unix, and which includes Mac OS and Linux, ipconfig/all on Windows. Looking at the ifconfig-a output, and I've selected out the Ethernet 0 interface here so I can make it a little bit larger. Again, we have the Ethernet address with the 48 bits, and then we have multiple IPv6 addresses. We have an IPv4 address, another IPv6 address. We have a total of 5 IPv6 addresses, and one IPv4 address, one Ethernet address on this interface. The status is active. It is an active interface. The media is auto select, which is refers to the Ethernet capacity ability to dynamically pick your speed, whether you're running at 10 megabit or 100 megabit or gigabit. And the MTU, the media transmission unit, is 1500 octets, which means that in one Ethernet frame I can send an Ethernet frame of maximum size 1500 octets, which is common for Ethernet. I've said this before, I'll say it again. The MAC address is also called the hardware address or the Ethernet address, and those terms are used interchangeably. It's 48 bits. The first 24 bits indicate the Ethernet card manufacturer's organizationally unique identifier. So if you Google search on OUI identifier and pick one of the OUI lookup tools, you can find a web interface where you can type in the first 3 octets, the first 24 bits of the MAC address, and it will tell you the manufacturer of that Ethernet card. In this case, the manufacturer of the Ethernet card is Apple. Modern Ethernet has improved substantially on the old bus-style Ethernet. In a modern Ethernet network, you have a central hub or switch, and you connect hosts to it in a star pattern using twisted pair cabling, which could be Cat3 at 10 megabit, Cat5, Cat5e, Cat6, Cat6e, and so on. Hubs repeat all frames to all hosts, which can still possibly result in collisions, which is bus-like. But one broken wire does not break the entire network. So that even a hub is a substantial improvement over the old bus topology. Switches selectively repeat frames to destination hosts. That decreases bandwidth usage. You can or improves bandwidth utilization. So for example, the host in the top left could be transmitting to the bottom left, and at the same time the host in the top right could be transmitting to the bottom right. And both of those communications could go on simultaneously. Switches can store and forward frames, which can also help to eliminate collisions. So if the top right and the top left both transmit to the bottom right at the same time, the switch will store both of those frames and then transmit them sequentially to the bottom right, eliminating a collision. Switches can also enable simultaneous transmissions and receptions. So a host can be sending a frame and receiving a frame at the same time. And then another host could be sending a frame and receiving a frame. That's called full duplex, as opposed to half duplex, where a particular host can send or receive. The old buses and hubs are half duplex. Switches can be half duplex or full duplex. Most networks today are built out of full duplex gigabit switches. Wi-Fi standards are also from the IEEE and start with 802.11 as opposed to 802.3. Wi-Fi standards are, at least to the computer, look very similar to Ethernet. Stations transmit when they detect that the channel is idle, so they have the carrier sense. Multiple stations can access the Wi-Fi spectrum simultaneously. That's multiple access. They detect when a collision occurs, or they try to avoid collisions, so it's called collision avoidance. Carrier sense, multiple access, collision avoidance. The primary spectrum, there are two major bands, the 2.4 gigahertz band and the 5 gigahertz band, and major standards which you may have heard of: 802.11a, 802.11b, 802.11g, 802.11n, and then the newer 802.11ac and very new 802.11ax standards. So multiple hosts are talking with the Wi-Fi access point. One tool, at least on Mac OS, is you have a Wi-Fi icon at the top right of your Mac. If you option left click on it, then you can pull up information about your wireless network, not just the IP address and the router, not just your IP address and the router IP address, but the security level, the MAC address of the wireless access point, the channel, which includes the band. You can see this is in the 5 gigahertz band. The country code, because different countries have different frequencies that are allowed for wireless. You can show the signal strength, with negative 51 dBm is pretty good. You have the noise level. You want your signal strength to be bigger than the noise level, and it looks like it's smaller, but remember these are negative numbers, so negative 51 is bigger than negative 92. We have the transmission rate and 877 megabits per second. Not that we'll ever get close to 877 megabits per second in reality, but when we're actually transmitting bits into the spectrum, that's the rate. We won't actually achieve that throughput because of collisions and because of other hosts and because of all the overhead. The physical mode, 802.11ac, so we're running the 802.11ac standard here, which is pretty good and pretty recent. And then the MCS index along with the physical mode results in the transmission rate. Let's go back to the Ethernet 2 frame format as it's seen by the CPU on the host after it's passed up by the network interface card. It starts with the destination MAC address, 6 bytes, 48 bits. Now that feels wrong. Most of the protocols we deal with start with a source address and then have a destination address. The Ethernet frame is different. It starts with the destination MAC, and that way the Ethernet cards, when they're reading the frame, as soon as they get 48 bits into the frame, they know whether the destination MAC address is one of the ones that they need to listen to or not, and if it's not, then it can just ignore the rest of the frame. It doesn't need to worry about it. But so remember, Ethernet 2 frames start with the destination MAC address. Then we have the source MAC address, 6 bytes, 48 bits. We have the type, 2 bytes. The type has to be greater than 1500 decimal, which is 0.5 DC in hexadecimal. Because if it was below that, then it would be a length and it would be a different type of Ethernet frame format. And then we have the data encapsulated by the Ethernet frame, which can be from 46 to 1500 bytes, and it will add padding as necessary. Let's look at those type values. Again, if the type value is below a certain value, then it's another protocol, not Ethernet 2. If the type value is 0800 in hexadecimal format, then the data is interpreted as IP version 4. If the type value is 0806 in hexadecimal, then the data is interpreted as address resolution protocol, which is we'll learn about that later. There are multiple other historic types. AppleTalk is historic, DECnet is historic, IPX is historic. If the type value is 86DD in hexadecimal, then the data is interpreted as IP version 6. Now, one interesting thing about this is you can have an Ethernet network and multiple, Ethernet is a layer 2 protocol. Multiple layer 3 protocols can run on top of Ethernet. You can run IP version 4 and IP version 6 simultaneously. In addition, the address resolution protocol, it's another layer 3 protocol, although it's a helper protocol for IP version 4. And you occasionally, on some networks with older systems on it, you might find some of these other protocols on it. You might see some historic IPX, or if you have a really old Macintosh, you might see some AppleTalk. So it's interesting that you could run multiple layer 3 protocols on top of layer 2 Ethernet. Let's manually decode an Ethernet frame. So here is the frame contents in hex, and we're not including the preamble and we're not including the FCS. This is as passed up to the host CPU by the network interface card. And keep in mind the frame is transmitted as bits. Each hexadecimal character corresponds to 4 bits. So what is the destination MAC address? Well, here is our Ethernet 2 frame format, and the destination MAC address is the first 6 bytes, which is the first 12 hexadecimal characters, because each hexadecimal character is half a byte. So 68, 5B, 35, 89, 0A, 04. That is the destination MAC address for this Ethernet frame. What is the source MAC address? Well, that is the next 6 bytes. So the next 12 hexadecimal characters. So the source MAC address is C8, 69, CD, 2C, 0D, 50. What is the type or length field? And the reason I say that is I've been talking about these other Ethernet frame formats. It's either the next 2 bytes are either a type or a length, depending on the value. The type or length field in a hex is 0800. Is this Ethernet 2 or 802.3? Well, 0800 is greater than 05DD. So this is Ethernet 2. And so we read the 0800 off of the ether type numbers, and we can see that 0800 means IP version 4. So this is an Ethernet 2 frame. We know our destination MAC, we know our source MAC, and we know it includes IP version 4 information in it, and we know the IP version 4 information starts right here. Here is the solution for the prior frame decode with the destination MAC, the source MAC, and the type field color coded, so you can see them, and then where our IPv4 information begins. I have bad news and I have good news. The bad news is I am going to ask you to do manual frame decodes on the quizzes and exams. The good news is when I do that, I will give you the Ethernet 2 frame format, and I will give you the ether type table, because this class, we're not expecting you to memorize all the different frame formats. That would be silly. But we do want you to be able to understand the frame formats and demonstrate your ability to manually decode an Ethernet frame given the frame value and given the frame format and given the ether type numbers, so you can decode the contents.